All right, so another topic in section 5.4 is something called the mean value theorem for integrals. So we did a mean value theorem for derivatives, and basically that one said that if you have a function which is continuous and differentiable on an interval, then somewhere on that interval you will have an x-coordinate where the slope of the tangent line is equal to the average rate of change on the interval. So that would be like the slope of the secant line. Now, the mean value theorem for integrals is kind of similar. It's saying if you have a function which is continuous on an interval, then there will exist an x-coordinate somewhere on that interval where the integral of the function, the integral of the function over the entire interval is equal in value to the function value at that x-coordinate just times the length of the interval. So what this is basically saying is that here's your function on an interval from, let's say, a to b, like this. And it's saying that if you calculate this area under the curve here, there will be some coordinate in the middle here, somewhere in between a and b, possibly equal to a or equal to b. But there will be some coordinate where if you find the height of the function and then come in here and just take this height and make a rectangle, right? Multiply that height by the length of this interval. This right here would be the area of a rectangle of height f of c. It's saying that the area of that rectangle will equal the area under the curve, which would be this other one, like that, right? And you can kind of see based on my picture, the whole idea here is that there will be some region, there's some portion of the curve which is above and some portion of the curve which is below, and they're going to cancel each other out. They're going to kind of, basically balance each other out. So I like to think of this as the Goldilocks theorem for integrals, because there's a proof of this that kind of reminds me of Goldilocks and the Three Bears. So let's take a look and see. I'm going to look at three versions here. Okay, so let's say this is our function. The curve here is our function, and we're looking at the interval a to b, a to b, a to b, a to b. Okay, so this is just three pictures of the same thing. On the one hand, one thing you could do is to find the lowest point on that function. You could do an optimization process and find the minimum, the absolute minimum on this interval. You could do you could do the closed interval method, for example. Okay, if we did that and then we made a rectangle at that height, all right, then that rectangle, that is too little. That's too little, right? That area, or the value of there will be less than the actual, the correct integral, right? Because there's this portion over here which is going to be we'd have to add on, right? So we fall short. On the other hand, let's look at the other extreme over here. If you took the maximum on this interval, okay, and then calculated the area of a rectangle at that height, like this, okay, this is clearly too much, right? Because you have this region here, as well as a little bit over there, you can see, where you'd have to subtract that off to get back to the correct, the correct integral. So that's too little, that's too much. Now, if you were to vary the height of this line, this dotted line, vary it between too little and too much, this is less, this is more, somewhere in between, you're guaranteed to hit the exact correct height that will cause the the plus and the minus to kind of balance each other out. I didn't draw that very well. Let me draw it slightly better. I think it needs to be a little lower down here. There's a perfect height there, where you're gonna have a portion here. Let me see here. You're gonna have a portion here that you'd have to subtract off, negative. But then you'll have a portion here that you'd have to add back on again, like this, above and below. And they don't need to be contiguous portions, they could be kind of scattered around. You could have parts where it goes above and parts where it goes below. As long as they all balance each other out. If they balance each other out perfectly and cancel, if these pluses and minuses, regions all cancel each other out in area, then what you have is a situation where the area of this rectangle is exactly equal to the definite integral over the like the area under the curve over that interval there. So this is just right. Hence the Goldilocks analogy. Okay, so another key takeaway from this is that the function value you found, okay, the f of c value that you found right here for this c, which you found right here, right, that f of c actually is the average value of the function on the interval, which is why it's called the mean value theorem, because mean means average. So this mean value theorem then extends to an idea called an average value formula. So if you want to calculate the average value, that's the f of c. All you've got to do is divide both sides of this equation up here by b minus a, and you will get a formula to calculate the average value of a function on an interval. So I'm going to talk about that in the next video.